Okay, so now we have our solution to the PDE. I'm not going to scroll all the way back up there, but we want to apply it to this special case where we're looking with initial data of this very special form here. So let me just remind you let me get my microphone situated. The solution u of xt. Okay, so notice here alpha is equal to 1. So u of ft is equal to 1 over the square root of 4 pi t times the integral, the initial data, which is going to be f of y, e to the minus x minus y squared over 4t dy. And that's a y. If we want to, we could write this a little more concisely. Sometimes it's helpful to sort of abstract and think about it just in this way: f of y, times the fundamental solution, x minus y, t dy. Okay, they both have their advantages and disadvantages. Okay, so now what we're going to get is, all right, now what is f? F is 0 when x is less than 0, and it's equal to 100 when x is greater than 0. Okay, so what does this give us? This is just going to be the integral from 0 to 100, sorry, not 0 to 100, 0 to infinity. F is 100, so that's 100, and then times the fundamental solution. Whoops. Okay, sorry about that. There's a lot going on. I don't know if you heard the noises before. Anyways, okay. So now there's a couple of ways to approach this problem at this point. One way, I think maybe the most straightforward way is just to replace phi with what it is. So I'm going to pull this 100 out of the integral. And so now we're going to have the integral from 0 to infinity. And then I'm just going to put all of this in the integral. So e to the minus x minus y squared over 4t, and then we divide by the square root of 4 pi t dy. Okay, and I'll make a change of variables here. I'm going to say z is equal to x minus y over the square root of 4t. So then that way z squared, I can just replace that whole exponent there with z squared, or minus z squared. Okay, and if this is the case, then dz is equal to minus dy over the square root of 4t. So now let me make my replacements over here. So I'm going to have 100. Okay, how are the limits in the integral going to be replaced? Well, z is equal to x minus y over the square root of 4t. Okay, so down here below, y is equal to 0. So these are my y limits. So that means my z limit, my lower z limit, is going to be x over the square root of 4t, and my upper limit is going to be x minus infinity. So it's going to be minus infinity here. And then I'm going to have e to the minus z squared. And notice dz is equal to minus the square root of 4t times dz. So I'm going to keep my square root of pi here, but this is now going to be minus dz. Okay, so I've got a negative that I'm multiplying the integral by, and I have this weird thing where I have minus infinity in the top limit. Remember, whenever you multiply the integral by minus 1, you can switch the order of the limits. So overall, this is going to be equal to 100 times the integral from minus infinity to 0, minus infinity to x over the square root of 4t. Okay, but now I'm going to be integrating the function e to the minus z squared over the square root of pi dz. And I'm going to split this into two pieces, one going where the integral goes from minus infinity to 0, and one where it goes from 0 to that upper limit. So this is going to be equal to 100 times the integral minus infinity to 0 e to the minus z squared. You could also just write this as the phi function for an appropriate value of t. And then plus the integral from, sorry, I forgot the 100, plus 100 times the integral from 0 to x over the square root of 4t e to the minus z squared over the square root of pi dz. Okay, now what are we going to get? So this integral right here, so if I integrate from minus infinity to infinity, I get 1. Integrating from minus infinity to 0, this is just 1/2. Because we're just integrating a Gaussian, half of a Gaussian basically, from minus infinity to 0. So that's 1/2. You multiply by 50, you get 50. And then really, what we have here, there's really not a whole lot more that we can do here. I'm going to pull out the square root of pi here. And this is going to be the integral from 0 to x over the square root of 4t e to the minus z squared dz. And that's about all that we can do. There's now, to compute this, we're going to actually have to do a numerical computation or something along those lines. But I just want to point out two things here. The solution is non-zero for any t greater than 0. The solution u of xt is never equal to 0. In fact, we see it's at least going to be equal to 50 at any point on the whole real line. So even though the solution, even though there's only concentration from 0 to infinity, and it's 100 there, everywhere along the real line, the concentration is at least going to be 50 there for any positive value of time. Okay, so again, this infinite propagation is a completely different phenomenon than what we have seen with the wave equation. The other thing that I want to point out is that the solution, u of xt, notice that the only way that the variables x and t come into play here are with the ratio x over the square root of 4t. So what this tells us is that u of xt is some unknown function of x over the square root of 4t. Okay, so now what we can do is we can take this and plug it into the PDE. And let's see what happens when we take our expression and we plug it into the PDE. Probably going to need an extra sheet here. That's going to make me scroll. Just giving you guys a little behind the scene look here. Okay, all right, so if I take the t derivative, so the t derivative of u, if u is defined this way, the t derivative of u is going to be, well, I'm going to have to do the chain rule, right? So it's going to be x over minus x. Sorry, let me just be a little more careful here. Okay, so the derivative of the inside is going to be, just to make explaining this a little bit easier, I'm going to write this as x over 2 times the square root of t, like that. And so when I do the derivative of the inside, we're going to get minus x over 4 times t to the 3/2 times f prime of x over the square root of 4t. Or let me just write it again to keep things consistent. Let me write this as 2 times the square root of t. Okay, and then the x derivative, now I'll go down to the next page. The x derivative of u. Okay, well, what am I going to get then? Again, it's going to be chain rule the derivative of the inside. I'm going to have 1 over 2 times the square root of t times f prime of x over 2 times the square root of t. Okay, but I need the second derivative, so now I'm going to take the second derivative, so it's just the derivative of what I have up there with respect to x. And now we're going to get 1 over 4t times f double prime of x over 2 times the square root of t. Okay, so now putting these together, these two things should be equal to each other. So we're going to have minus x over 4, I'm going to write it this way, over 4t times t to the 1/2 is equal, times f prime, of x over 2 times the square root of t. This is going to be equal to 1 over 4t times f double prime of x over 2 times the square root of t. Now, if I multiply both sides of this equation by t, what you end up with is the following. You're going to have minus x over, and I'm going to put the 4 back in there. So it's going to be minus x. I want to multiply it by 2t. So multiplying it by 2t, what we're going to end up with over here is minus x over the square root of 4 times t, f prime of x over, now I'm going to put everything back in, over the square root of 4 times t. Okay, and then over here, if I multiply by 2t, I'm just going to be left with 1/2 times x double prime of x over the square root of 4t. Okay, so now I'm going to introduce a new variable. I'm going to call it c, and this is going to be equal to x over the square root of 4t. And so now the above equation can be written in the following way. This is going to be minus c f prime is equal to 1/2 f prime. Let me write the variable. This is of c. The variable here is c. So this is c is equal to 1/2 f double prime c. Okay, I'm going to switch colors here. So now I can rearrange this, and this is going to give me f double prime of c over f prime of c. Okay, what am I going to get when I do that? I'm going to get minus 2c. Okay, but now the left-hand side is the derivative with respect to c of natural log of f prime of c. And then this is equal to minus 2c. Now I'm going to take the antiderivative of both sides, and we get log f prime of c is equal to, okay, it's going to be c squared over 2, so minus c squared plus some constant. I'm going to raise both sides to the power of e, and what you get is f prime of c is equal to some constant times e to the minus c squared. Integrating again, so now I want f, so I've got f of c minus f of 0 is going to be equal to the integral from 0 c times the derivative, so it's going to be a, and I'll use the dummy variable z, e to the minus z squared dz. And then what is this? This is going to be equal to 0. Well, what's c? That is, if I come up here, I don't know, x over the square root of 4t. So this is going to be a times x over the square root of 4t, e to the minus z squared dz. So altogether, this gives u of xt. Remember, this is equal to f of c, right? U of xt is equal to f of c. So this then, because c, if you come back up here, what is c? It's x over the square root of 4t, and that's exactly what we have here, x over the square root of 4t. So now this is going to be equal to f of 0 plus a times the integral from 0 to x over the square root of 4t e to the minus z squared dz. Okay, sorry, I needed to add one more page. Okay, so now how can we figure out, f of 0, this is just a constant. This is just an arbitrary constant, right? It's arbitrary in the sense that we need to find it. So I'm just going to call this b. Okay, so how can we find this? Well, let's do something here. Let's just think kind of not very rigorously, but let's just think what happens when we plug in t is equal to 0. So let's look at two cases. Let's look at the case where x, I want to use a different color. So now I want to find what b and a are. So let's look at case 1. Case 1 is going to be x is greater than 0, and we plug in t is equal to 0. Okay, now plugging it into the formula is kind of hard to imagine what that means. I know one thing. I know u of x 0 has to be equal to 100 if x is bigger than 0. On the right-hand side, b, that's kind of obvious what that is. It's just b. A, we're going to write down. Now, if t is equal to 0, this is going to be like x over 0, a positive x over 0, which we can kind of think about as being infinity. So this is going to be equal to 0 to infinity, e to the minus z squared dz. But this is very close. We're very close to knowing what this integral is. In fact, if I multiply by the square root of pi and divide by the square root of pi, that integral with the 1 over the square root of pi is equal to 1/2. So I have 100 is equal to b plus the square root of pi a. Okay, on the other hand, if I look at, let's say, x is less than 0 and t is equal to 0, well, what am I going to get? Well, I'm going to have 0 on the left axis. It's the initial condition is 0. Is going to be b plus, okay, now x is negative. So x is negative, and I divide by 0. We can think about that as being negative infinity. So this is going to be a times the integral 0 to minus infinity, e to the minus z squared dz. But I don't really want to have minus infinity in the top limit. So this is equal to b minus a times the integral from minus infinity to 0, e to the minus z squared dz. I can now, as above, multiply and divide by the square root of pi. And so now this is b minus the square root of pi a. All right, so now I have this system of equations. I've got 100 is equal to b plus the square root of pi a. And I've got 0 is equal to b minus the square root of pi a. Okay, so what's the solution? If I add them together, it gives me 100 equals 2b. So in other words, b is equal to 100 over 2, otherwise known as 50. If I subtract the bottom equation from the top equation, that's going to give me 100 is equal to the square root of pi is equal, it gives me 100. It gives me 100. Let me just write this down. 100 is equal to 2 times the square root of pi a. So in other words, a is equal to 100. Sorry, I just realized I made a mistake. So this is over. So that integral is equal to 1/2. So sorry, divide that by 2, and I'm going to divide this by 2. Okay, so I could see that my answer wasn't going to give me the right thing, so I knew I had made a mistake somewhere. Sorry about that. Okay, so now if I subtract the second equation from the first equation, so again I need to divide that by 2, that by 2. If I subtract the second equation from the first equation, this is going to give me 100 is equal to the square root of pi times a. So a is equal to 100 over the square root of pi. If I come back up here, I'm going to plug 50 in here. And here I'm going to plug in, what am I going to plug in here? It's going to be 100 over the square root of pi. Okay, and then that is the solution. This is the solution that we got before. Okay, so we were able to take this alternate approach to finding a solution to the diffusion equation by first knowing, or by looking at the formula, first suspecting that the solution should be of a particular form, something like a function of x over the square root of 14. Okay, but we kind of have to solve, at least the way we did it here, we had to solve the PDE. We had to solve the PDE first to be able to do that. And so the question that I'm trying to ask here is this just a curiosity that we're able to do this, or can we somehow know this fact? Is there a way to know this fact without solving the PDE to begin with? And the answer is that there are ways to sort of predict that this is going to be the case just by looking at the PDE before solving it. Okay, so what I mean is the following. So we've got the t derivative of u of xt is equal to the x derivative of u of xt. And we want to see how this relates to various scalings. So let's say I define a new solution, a new function, v of xt, and I want to think about scaling the x variable and scaling the t variable. So let's just look at something that's not going to work. If I do something like lambda, if I have this new solution, lambda x, lambda t, or this new function, my question is, does this satisfy the PDE? Okay, well, let's think about this. Let me take the t derivative. If I take the t derivative, I'm going to get lambda, because I have to do the chain rule. It's going to be lambda times the t derivative of v. So this is the t derivative of v. If I take the x derivative of v, u. Sorry, let me be more explicit. Let me not just write random stuff here. Let me actually write what I'm saying. So the t derivative of v is equal to lambda times the t derivative of u. The double x derivative of v, okay, I'll let you guys think about this, but the double x derivative is going to be equal to lambda squared times the x derivative of u. Okay, so if the t derivative of v is not equal to the double x derivative of v, because in the t derivative I have a lambda, but in the x derivative I have a lambda squared. Okay, well, there's an easy fix. I'm going to put, instead of just lambda t, I'm going to do lambda squared times t. And then when I do the t derivative of v, I'm going to get lambda squared. And now if I define v this way, these two things are equal. If u is a solution to the diffusion equation, then v defined this way is going to be a solution to the diffusion equation. So if u of xt is a solution, then v of xt equals u of lambda x lambda squared t is a solution. Okay, so now notice what this tells us then. So this gives us some idea about the ratio of powers of the x coordinate over powers of the t coordinate. So notice if I have x divided by the square root of t, okay, and if I do this scaling and I do the same thing, so I'm going to have lambda x divided by the square root of, divided by the square root of the t coordinate, which is lambda squared t. Well, what am I going to get? I'm going to get lambda x in the top, and in the bottom, I'm going to get the square root and the square cancel, lambda times the square root of t, which is just equal to x over the square root of t. Okay, so this somehow tells us that the ratio x over the square root of t should come into play, which gives us a hint that we should be looking for solutions, that there could be solutions. Not every solution can be, not every solution has this form, but it does give us the hint that there might be some solutions that are just a function, more or less, of that variable there. Okay, this last part was a little bit hazy. If you want to learn more about it, these are called similarity solutions. And what we can actually do, we can actually derive the fundamental solution using, or we can, find the fundamental solution using these similarity solutions. But I'm not going to say any more about that. This video has gone on long enough.